Welcome back to Short Text 331. Today we are going to talk about vector coordinates and change of basis. So far we've talked about vector spaces quite a bit, and we said that vectors are simply the elements of a vector space. And we talked about the structure of a vector space and how it's made out of these objects we call vectors, and we need a set of scalars as well, and so on. And examples of these objects could be all sorts of things like triples, like this, triples of numbers. Here are real numbers, and so on and so forth. But examples of vectors could also be monomials of this form, 1x squared, and so on. But it could also be functions like sine of x and so forth. So there are very different kinds of objects that we could call vectors that would obey the definition of a vector space. Now, given a vector in our vector space and a basis, remember what we call the basis, that is a set of linearly independent vectors that span the vector space, then there will be, by definition, some constants ai, I called ai here, such that our vector can be written as a linear combination of the basis vectors. So the basis goes from w1 to wn. That means that our vector space is n-dimensional, and by definition it spans the vector space. And so spans means precisely this, that any vector, here a particular vector we picked, can be written as a linear combination of the basis vectors. And these constants ai, which exist by definition of what we mean by basis, are what we call the coordinates of v in the x basis. So these coordinates depend on the vector we're talking about, but they also depend on the basis. Okay, and once we chose the basis and we choose the vector, then those coordinates are fixed. But what if we choose a different basis? If we choose a different basis of vectors u1 to un, then there will be another linear combination, which will also depend on the vector and the basis. And so there will be different coordinates, b sub j, that are the coordinates of v in the y basis. So you see the coordinates will change, even though when you add it all together, you get the same vector that we're interested in. So that's a fixed vector v. So we can express it like this in our x basis, or we can express it like that in our y basis, and the coordinates change. And so for a given problem, some coordinates may be more convenient than other coordinates to represent the vector v. We may want a basis that is nice and orthogonal or orthonormal, and that could be the basis y, for example. And so we may like that basis better than a non-orthogonal basis, which could be our basis x here. And so it is useful to know how to change from one set of coordinates to another set of coordinates. That is what we call a change of basis. So from the basis x to the basis y, and maybe vice versa. We may want to be able to go back and forth from one basis to another basis as a matter of convenience. And it turns out that this idea of being able to change from one basis to another, but not changing the resulting vector, is actually very important in physics. The fact that we have the ability to describe nature in any way we want, with any basis we want, and nature stays the same, then is really a central concept in relativity, and also is very important in quantum mechanics as well. And in relativity, we talk about boosts and changes of coordinates and coordinate frames and so on. That's really a change of basis. And then what nature does is represented in this analogy by the vector v. So the vector v here remains the same, but we represent it in different ways with different kinds of coordinates, which I call here ai and here b sub j. So in that sense, then the vector v has a life of its own, regardless of how we choose to describe it. So the vector v can be chosen to be described with the basis x or with the basis y, and by itself has a life of its own. And so we refer to v as the abstract vector. If we want to be specific, we can choose a set of coordinates, a basis that is, and we'll have some coordinates, but otherwise it's just v itself. And the v then we refer to it as the abstract vector. And at this point, I want to say that this is a series of videos meant for my students at UNC Chapel Hill. If you like these videos and you're enjoying this series of videos, please consider liking and subscribing to the channel. And if you're not a UNC student, but you're looking for a tutor in physics or math, in English or in Spanish, you can contact me at shorttakes331@gmail.com, or you can leave a message in the comments section below. Now, since there are different bases that we can choose from, here I called x and y, but there's an infinite number in reality, we may want to switch from one to another. And like I said, that's typically very useful. So how do we do that? So we'll see how to do that next. So take the basis y that has the vectors u sub j, and we note that we have to be able to write each of these vectors in terms of the other bases. Why? Because they're both bases. And so each of these guys, each of these u sub j is something that you can write as a linear combination of the w's of i's. And so we have objects here which are the coordinates of u sub j in the w basis, or in the which we call the x basis. And so they carry two indices, one index corresponding to the j index that's out here, and another index I, which specifies the specific coordinate associated with w sub I. And so we have this linear combination. So these objects are the coordinates of u sub j in the x basis, or if you want, you can say is the ith coordinate of the jth vector u sub j in the x basis. And so then for any vector v, though we can write in the y basis in this way, as a sum from j equals 1 to n of the coordinates in u sub j as we described before. This is simply the expression of v in the y basis. We can go ahead and insert this expression. This expression of the one basis in terms of the other basis, we can insert it in here. And so I do that right here. And then what we're going to do next is we're going to flip the order of the sums. We're going to pull this I sum outside and push this in. And we're going to separate as much as possible the j sum from the I sum. And we can do that. It's perfectly allowed to do that. The sums are finite. There's no infinity limit of any kind here, so this is perfectly allowed. And so we go ahead and we pull this one out here, and then this with b sub j is pulled in, and now we have something that's entirely dependent on j in here in the parentheses with the I index. And so this object is the coordinate of v in the x basis, and so it must be that this whole thing is actually a sub I, and we'll see how that comes about. We know that in the x basis the v vector is written as a sum from I equals 1 to n of a sub I wi, and so by virtue of this expression and this expression, these two things must be equal. They're both equal to the vector v, and so we can subtract one from the other and rearrange the terms, and we obtain this identity. We obtain that the sum, same sum here, a sub I minus this parenthesis here, which comes from here. Again, this comes simply from the fact that this v is the same as this v, and so this must be equal to this. So I put both things on the same side of the equation. That must be equal to 0. And so it must be then that this vanishes, equal to that each of these vanish. So each of these guys, for every I individually, these have to vanish. How do I know that? How is it possible? Why is it not possible that maybe some of the terms cancel against some other of the terms? Well, the reason we know that that's not possible is that the wi are linearly independent. So we have assumed that wi is a basis. And if it is a basis, then the vectors are linearly independent. And so it must be necessarily that the only way to have a vanishing linear combination is if each of the coefficients vanish. And so it must be that this whole thing is 0, which proves then that this sum is equal to this ai for each I individually. So then again, we stated here, for each I individually, a sub I is equal to this. And what this tells us is that in order to transform from the coordinates in the y basis given by b sub j to the coordinates in the x basis given by ai, we have to do this calculation. We have to do this sum from j equals 1 to n of these coefficients with tji. And so this tji, remember, are what relate the x basis to the y basis in this way. The x basis is related to the y basis in this fashion, tji. And we are reusing those here to flip the coordinates from the y basis to the x basis. So this is how you do it. So the coefficients tji that connect the x basis and the y basis serve to transform the coefficients or the coordinates b to the coordinates a. If we arrange this coefficients tji into an array like this, we obtain what we call a matrix. And this is the first, I believe, the first time I used the word matrix in this series, or one of the first times anyway, one of the only times. And then we would call that matrix T, and we would arrange it in this way: T11, T12, T13, and so on. And then we would have, in this case, because the sums go up to n, we have a matrix that is of size n by n. We say it has n columns and n rows. So this t11, t21, and so on goes down to tn1, and this top here goes to t11, t12, t13, and so on up to t1n. On the bottom here, the bottom right, of course, is tnn. These indices are such that the first index tells you which row you're standing at. So this is row 1, this is row 2, and so on up to row n. And the second index gives you the columns, and that's the convention across all of physics and mathematics. The first index gives you the row, and the second index gives you the column. We'll talk more about matrices in a future lecture and quite a bit in upcoming videos as well. So now, all the bases are in principle valid, so there's nothing preferred about the x basis versus the y basis. And so just like we flipped here, we switched from the y basis back to the x basis, we could have been interested in switching from the x basis to the y basis instead. We may be interested in the reverse operation, and so it must be that it is possible to write this as well. The reverse operation will exist as well. And so just like I call T here, this operation of combining all the B's to get each of the AIs, it is possible to do the opposite, to combine all the AIs in certain ways with these coefficients to get each of the B's of K's. So there must exist coefficients that satisfy that, and those coefficients are actually the ones that relate the U basis, or which I call Y basis, the Y basis with U sub j elements, to the W I basis, which I call the X basis. And this is simply renaming things if you want. If I choose to rename the A's as B's and the B's as A's and so on, and W's as U's and the U's as W's, it's simply renaming of everything. But in reality, what this represents is the inverse operation. You can have a basis X and choose that to be the basis where you start, and then you go from X to Y, or you could choose, for whatever reason, to go backwards. You may need to go backwards from Y to X. So both of those operations exist if you have two well-defined bases, X and Y. And here I call the operations, or rather the operations are encoded in these matrices that I call T here, and there will be another matrix U encoding this transformation that combines all the AIs and gives you the BKs as a result. Now, if this is true, if this transformation exists, then I could go ahead and take the B's of K's, which are the sum of I equals 1 to n, as you see here, and you have uik, and I have that here, but the AIs, as we saw, are given by this sum. Let me go back up and show you. So the sum, so the AIs are given by the sum over j of B's of j tji, and I'm inserting that now in this expression. What happens if I do that? Well, then I get this sum to be presented in here, and now I'm going to again switch the order of the sums, and you'll see what I obtain. So I pull the sum over j to the outside, b sub j to the outside, I get the sum over I in here, tji uik. Now, this is a little strange. It seems that I'm relating the b's to the b's, and there's no reason to do that. The b's are simply the b's. b1 is equal to b1, b2 is equal to b2. There's no reason to form sums over all the b's of j's of any kind to get b's of k back, right? If on the left here it says b1, the right should say b1. There's nothing else. It's not a different set of coordinates. It's the same coordinates. And this is true for any b's, any values of b whatsoever. So it must be that these numbers somehow combined all together in this sum. All this stuff really becomes is 0 for all cases here except when j is equal to k. And so then I get bk equals to bk. And that's indeed what happens. These numbers give you, as a result, what's called delta jk. So they're equal to 1 if j is equal to k, and they're 0 otherwise. And this is what we call the Chronicle Delta. This object is called the Chronicle Delta. It's an object that is equal to 1 if j is equal to k. So 1, 1, 2, 2, 3, 3, and so on. That's 1. That gives you 1 as a result. But otherwise, this delta jk is 0. So if you try to evaluate delta at 1, 2, or 2, 1, and so on, it is 0. And that completely specifies the values of this object. And this is how we define it. This is the definition of the Chronicle Delta. So it must be then that since this identity is true for any coordinates bk whatsoever, and these objects don't depend on the coordinates, these objects are simply given by the basis. The bk and bj depend on the vector, but if you vary the vector, these bk and bj will change. There could be all sorts of weird things, but nevertheless bk must always be equal to bk. So b1 is just b1, it's nothing else. So it must be then this is simply delta jk. And so that is what I wrote here. And really what's going on here is simply the expression that the operation of transforming from coordinates x to y and the reverse operation from y to x, if you do one and then you do the other one, then you end up right where you started. You haven't made any change. That's really what's behind the scenes here, that performing one operation and performing its inverse gives you back where you started. And that's why I'm saying bk should simply be equal to bk. b1 is b1, b2 is b2, and so on. There should be no need to do any sum or anything. And so this object simplifies this whole sum entirely and tells you that the only term that survives in here is the one where j is equal to k, which is what we have on the left-hand side, as expected. Now, if we write that in matrix form, what we would say is that the product of the matrix T with the matrix U, whose elements are given by these objects here, is equal to 1. And this 1 is a matrix that we call the unit matrix. It has 1 in the diagonals and 0 everywhere else. This is reflecting this definition here of the Chronicle Delta. And then we say that U is the inverse matrix of T. And so we write U as T to the minus 1. So that means that U is the inverse of T. It's not true in general that for any matrix there will be an inverse. There are certain conditions that a matrix has to satisfy to have an inverse, that is to have a matrix that accompanies it such that when you multiply the matrices, meaning this, you would obtain the Chronicle Delta, meaning the identity matrix. We'll talk more about matrix multiplication in the next video, but I want to say here that for matrices T and U that represent changes of basis from, for example here, an x basis to a y basis, then it is always true that there is an inverse. So you can always change from one description of a vector to another description of a vector, from one set of coordinates to another set of coordinates, but you can always do the reverse operation. That's always possible. And what's behind all that is that a basis is linearly independent and spans the whole vector space. Because you have those two things, then this is guaranteed that the inverse always exists. So let's see an example of change of basis to fix the ideas. So suppose that our vector space is R2, yeah, so the plane R squared, and let's say that our basis X is made out of two vectors W1 and W2, and the vectors are given by 2, 0, 1, 3, and there's another basis Y, U1, U2, where the vectors are U1 equals 1, 1, and U2 equals 1 minus 1. It's very easy to check that these two vectors are linearly independent. There's two of them, and so we know that they span R2, which is a two-dimensional space. So that's enough to describe the whole space. And these two are also linearly independent. It's very easy to see. And moreover, there's again two of them, so they span the whole vector space. So these two sets, W1, W2, and U1, U2, are both well-defined bases for any vector we want to represent in 2 dimensions. And in this space of real vectors in 2 dimensions. And so U1 now can be written as in terms of the other bases. So we can write U1 in terms of W1 and W2. So how do we do that? Well, we use these T objects, T11 W1, T12 W2. Remember, the first index here has to do with this vector, and the second index is what accompanies this basis vector. And it's very easy to see, if you do this calculation on the right, that you get 2 T11 comma 0, and then coming from here, and then T12 is multiplied by 1 and by 3, and so you get this result. And adding it all together, you get, for the first component, 2T11 plus T12 coming from here, and the second component we get 0 from here, a 3T12 from here, and so we get 3T12 down here. Now we want that to be equal to 1, 1. Why? Because that's U1. That's the U1 guy here. So 1, 1. So we have to force this whole component to be 1, and we have to force this whole component to be 1. If we do that, it's very easy to see that T12 has to be 1/3, And so we insert that in the other equation, and it's very easy to see that t11 is also 1/3. If I did the calculation here correctly, you can of course go ahead and check it and see that I did this right. Sometimes I make mistakes, so you should always check these things, and you should check it because it's a good exercise as well. Now we repeat the process with u2. u2 is a vector 1 minus 1, and if you go through the same process I did before of symbolically calculating the result of adding these two terms and force that to be equal to 1 minus 1, you obtain that t22 is minus 1/3 and t21 is 2/3. And so what that tells us is that we can arrange the objects Tij into a matrix that looks like this. So the 1/3, 1/3 comes from these two objects here. Remember, row is the first index and column is the second index, so we get 1/3, 1/3. And here we get minus 1/3 for t22 and 2/3 for t21. So that's our matrix T. Great. So now, as an exercise, you can find the matrix U corresponding to the inverse operation. And what that means is that you would have to repeat this exercise where now you're trying to represent W in terms of U and W here in terms of the U vectors. And instead of having the T matrix here, you would have the U matrix that I used before, which would correspond to the inverse of this matrix T. And we'll talk more about matrices next time, like I said. But to finish up, I want to talk a little bit about a different kind of example. I've been talking quite a bit about how vectors are not only these objects that have components, like we see here, 2 components or 3 components in 3 dimensions, or an arbitrary number of components, but also vectors can be functions, and that's very, very useful in physics. And so it's important to see some examples in that direction. So suppose that we have a basis for a space of polynomials that is given by this. This is one of my preferred bases. It's very nice and easy to work with. And so we have our vectors be 1, x, and x squared. And so this would be if you want w1, w2, w3. And our y basis is going to be u1 given by 3, u2 given by x minus 1, and u3 given by 2x squared minus x plus 7. So this is some weird linear combination of these guys. And so let's see, let's really unfold this and see what it looks like. Well, 3 can be written as 3 times 1, obviously. And so this tells us that t11 is 3. This is the 1 here comes from the fact that we're representing this vector, and the other one comes from we're asking the coefficient of this guy. So that's 3, but there's nothing else in this 3 that points to x or x squared, and so this is 0 and 0 for t12 and t13. Now the story varies a little for x minus 1. So x minus 1 has a part that is a component in the direction of x, and a part that is a component in the direction of 1. In fact, is x minus 1 is 1 times x plus minus 1 times 1. And so that means that t21 is minus 1, t22 is 1, and t23 is 0, because there's no x squared component. Finally, if we take 2x squared minus x plus 7, we put it here, that is 2 times x squared plus minus 1 times x plus 7 times 1. And so it gives us a 2, a minus 1, and a 7 for each of the components. And then this would give us a 3 by 3 matrix, which you can read off right here. The components, if you read them by rows, are going to be 3, 0, 0, minus 1, 1, 0, and finally 2, minus 1, and 7. And that will be your T matrix that transforms this basis, or that connects this basis with this basis. Okay. And if you want to transform coordinates from one to the other, you would use that T matrix or its inverse. And so as an exercise, you should try to go ahead and calculate how to express these vectors as linear combinations of these vectors, and that will give you the U matrix. And then after you see the next video where we talk about matrix vector multiplication or matrix multiplication, you'll be able to multiply these two matrices T and U and see that you get the identity matrix, which verifies that indeed going from one basis to another and going back from the second to the first one gives you an operation that is trivial. It gives you just a unit matrix. It's like you didn't do anything. It's like you went from A to B and from B back to A. And that's all I have for you today. If you have questions or comments, please leave them in the comment section below. As always, if you find these videos interesting or useful in any way, please like and subscribe. And if you're looking for a tutor in physics or math in English or in Spanish, if you're not a UNC student, feel free to contact me at shorttext331@gmail.com, or you can leave a comment in the comment section below and I'll try to respond. Thank you very much, and until next video.